All right, 15c, instead of x, we've got our old friend from pre-cal, Mr. Theta, right? We're approaching 0, never not first, direct sub. What is secant of 0? Secant of 0 is, well, no, I think it's D and E, right? On the unit circle, 0 is here. The order pair is 1, 0. Secant is the reciprocal of cosine. Cosine of 0 is 1. The reciprocal of 1 is 1. Okay, so secant of 0 is 1. That's kind of an important one. I was making y'all's test this morning, writing questions for that test. That's Friday, and I came across secant of 0. And it was 1 this morning, and it's 1 right now, and it should still be 1 on Friday. So there you go. Okay. So 1 minus 1 is 0, and in the bottom we get 0 times secant of 0, which is what? What's secant of 0? 1. So 1 times 0 is 0. So we do get 0 of 0. Okay, so on Friday's test, everyone's going to get secant of 0 right. That's good. Okay, so now we have to get rid of the 0 over 0 problem. We have a theta in the bottom that's causing 0. There is no common factor of theta in the top. So none of those other methods, lick 'em over lick 'em, LCM, RATCON, none of them are going to work because it's got trig in it. Probably going to have to use one of the two that we memorized, the sine one or the cosine one. So if this were like a little trig proof, what would you do? If you only had identities in terms of sine and cosine, you would write everything in terms of sine and cosine, yes? So let's go ahead and do that. Rewriting the limit, secant is 1 over cosine, and then we got minus 1. So you can't bring that cosine to the bottom because it's part of 2 terms in the top. And in the bottom, you have theta times 1 over cosine, which is the same as theta over cosine. All right, so now if you want, you can do state change flip, but I'm going to do it a different way. We have a complex fraction, so now this kind of turns into a lick 'em over lick 'em problem, right? So our 2 miniature denominators are cosine and cosine. So I'll just multiply by cosine over cosine, which is really cosine over 1 over cosine over 1. This is just one of the ways you can eradicate the complex fraction. And then when you do, you distribute, and you get cosine over cosine is 1. Minus 1 times cosine is cosine. And in the bottom, there's nothing to distribute. You just get your cosines dividing out, and that leaves you theta. And so this is actually what we're left with, which we learned yesterday is equal to what? It's equal to 0, right? And remember, it doesn't matter if it's 1 minus cosine or cosine minus 1. It works the same way as long as the theta in the top and bottom, whatever that is, 5 theta over 5 theta, as long as they match, it's going to be 0, all right? So that one's equal to 0. All right, ready to keep moving? There's quite a bit more to go here, and then some summary. So part D, limit as x goes to 0. Direct substitution, what do we get? We get sine of 0, which is 0, and on the bottom we get 0 times cosine of 0, which is also going to be 0. All right, so it's always important then to figure out what's causing the 0. In the bottom, the x is causing the 0, and in the top, the sine of 5x is causing a 0, right? The 4 in the top is causing a 4, and what is the cosine of 2x causing when you plug in a 0? What is cosine of 0? 1. It's causing a 1. So let's go ahead and think about a problem like this, about separating the good people from the bad people, right? Just like we do in society. Let's lock up the bad people. We'll put them in a beefy bracket. Call that a jail cell. And then outside here, in wimpy parentheses, where they can still come and go as they please, because they have the freedom to do so, they're not bad guys, we'll put the other guys, okay? So we've got the bad guys causing 0 over 0 in beefy brackets, and then the good guys that are not causing a ruckus in wimpy parentheses. And we'll focus on these separately. Now, in the first one, you're like, man, that sure looks a whole heck of a lot like what we memorized to be what? 1, but it's not, right? So this is where you click your heels 3 times and you say, I wish there were a what in the denominator? A 5. So magically appears in the jail cell on the bottom bunk, a 5, which is legal so long as somewhere out here in the free world, in the numerator, you also put a 5, right? So what we did is we just not only cleverly multiplied by a clever form of 1, but we cleverly multiplied by a clever form of 1. We associated the 5 in two different places in that same term. Okay? And now I think we're ready to rock and roll, yeah? The first one, by memorization, becomes 1. And then the second one, by direct substitution, becomes 20 over 1, right? And so the whole thing comes out to be 20. So you can create what you need as long as you do it correctly by multiplying by clever forms of 1. So get the 0 over 0 guys in one spot, everything else that's not 0 over 0 in the other spot, and do it that way, okay? Now, I don't know if there's a way to generalize that one from what we started with. I mean, it ended up being the 5 times the 4, but will that always work? We got a cosine and 2x in the bottom that didn't even come into play. Go ahead and try this one then. Kind of the same idea. Kind of create what you need to use what we've memorized. Trig manipulation. So when you get complex fractions, you kind of like hooray, hooray, because your next step is always to get rid of those complex fractions. Make sure that 3x, remember, is in the top and the bottom, right? Yeah, they're two separate functions. Good, bless you. So now, like, what's causing the 0 in the top and bottom? You got to separate them. You're going to find here that in the previous problem, we had the sign part. And then on the other side of the equation, or the fraction, we had the x there. We were just missing a constant. You'll find in this one that maybe you're missing more than just a constant. When you have cosine and sine, make sure that you keep the angles with them. Is that cosine of 3x? Tangent, remember, is sine over cosine. You got it backwards. Cosine over sine is cotangent. So what you're going to want to write is sine of 3x over cosine of 3x. All right, I'm going to catch up with some of y'all because walking around, y'all are up to a good first start. Tangent of 3x is sine of 3x over cosine of 3x. So putting in terms of sine and cosine makes sense, especially because we've memorized things in terms of sine and cosine limit-wise, and then it's over sine of 4x. So from here, you can state change flip, where if you want to put that over 1, now you have a complex fraction. Lots of ways to do this. I'll multiply by cosine x, or 3x, sorry, all over cosine of 3x. Just one way to do it. State change flip also works nicely. So for me, the cosine of 3x is up here, divide out, and I'm left with sine of 3x all over sine of 4x times cosine of 3x. Okay, so walking around, a lot of y'all are at that step, which is good. So now the question is, what do we do from here? Well, what's causing the 0 in the top when you plug in? The sine of 3x, and similarly in the bottom, sine of 4x. The cosine of 3x, he's causing a 1. So he wishes sines would get their act together. So let's do this. Let's go ahead and separate it now. Now for the sine of 3x, we're going to put him in his own cell, and we're going to put him on the top bunk. In another cell, we're going to put the sine of 4x, and we're going to put him on the bottom bunk. And then out here in the wimpy parentheses, if you want to kind of keep the analogy going, we'll put the free person who's not causing a problem, okay? Now in this case, because they're both sines, I separated them in two separate things. We need to create now what we need to be able to use what we memorized. So in the first brackets, we wish there was a what in the bottom? We have sine of 3x. We wish there were a 3x. Well, boom, we could put a 3x there, right? So long as we put a 3x somewhere over here. Okay, and this is just one way to do it. I'll put a 3x over there. Now in the other one, I need a 4x in the top, which is fine so long as I put a 4x in the bottom somewhere over here. And I didn't have room, so I just put 1 over 4x. Right? That makes sense, yeah? It's all equal to 1. Okay, so notice I did introduce a couple of extra x's. I could have probably used this x here, there, but I didn't even bother doing that, okay? So what I can do now on this last piece here is these extra x's that I introduced, they actually do divide out. Okay, factor and divide out. And now I've created what I needed. I can just go all the way across and evaluate it. What's the first bracket become? 1. The second bracket, also 1, right? And now everything else on the outside, we just use direct substitution. That's going to be in the top a 3, and in the bottom, when I plug in a 0 for cosine of 3x, I get 1 times 4. So the answer ends up being 3/4. All right, so it's possible to do that, but we created it. It took a few steps. Now for this one, let's see if we can go to the top and generalize something. Our answer was 3/4. Do we have a 3/4 visible in the original problem? We sure do. Is that the same 3/4? Yes, it is. So we concluded yesterday at the end of class with this idea right here, that tangent in green and sine in blue, although they're different functions, they behave exactly the same way near 0. They both pass through 0, 0, and they both have slopes. We're going to talk about slopes later on. They both have slopes of 1, 45-degree angles. They both launch out of the origin at 45-degree angles. So essentially, for limits near 0, just like their function values are the same, their limit values are the same. So they become essentially interchangeable near 0, okay? So we can now summarize this right here. We'll summarize this. We can say the limit as x goes to 0 of tangent of, I'll say, ax over sine of bx is equal to what? A over b. Now, because sine and cosine are essentially interchangeable at 0, you can have any combinations of tangent and sine there. So you can have the limit as x goes to 0 of sine of ax over sine of bx. And guess what it's going to be? A over b. You can have tangent over tangent, and it'll be a over b. And you can have sine over tangent. So there's several combinations, 4 of them. They're all going to be a over b because tangents and sines near the origin act the same way. So you don't want to write all those down. I get that. So if you come down here, look at the third line right here. That summarizes it all. I used m and n's down there instead. Yes, absolutely. If you memorize it, right? If you don't have it memorized, you have to work it the way we did. But you can just skip straight to the answer. Yeah. You won't have to prove it, no. And they show up often enough that it's probably worth memorizing. So there's a lot to memorize, right? So if we memorize as we go and we practice, in the context, we can retain it a lot more easily. So these top 2 down here in this chart, those are the ones that we did yesterday. As long as the angles in the denominator match, whether they're sines or cosines, it's always 1, right, when they match. When they don't match, it's always m over n. Now, you could probably even get rid of the top line because if they do match, what is m divided by m? 1, right? So it's always just going to be the quotient of those 2 coefficients, right? So you can almost combine those into one rule. All right, and now we have the sine, tangent, sine combinations, okay? All right, so that's why there's so much to do here. All right, so with that in mind, right here before lunch, maybe the last one, go ahead and attack this one. Go get it. Any way you want. You could attack that one any way you want. Oh, I like that. That's a good way. Right? But everyone has their own way. I like that way too. Oh, yeah. So you actually kind of proved it, right? Yeah. You didn't look on his iPad, did you, Simon? No? Okay. That definitely works, right? We did the same thing we did in the last one. We just used a different identity. And you went right to the answer, so you had some other insight. Right? I'm guessing? Yeah. Everyone has to find their own motivation here, their own insight. Ooh. Well, I don't know. What are you basing that answer on?
I just scrolled down.
Oh, you scrolled down? Oh, okay. Is that what you did too? Oh, yes, he scrolled down. Okay. Bird, did you scroll down or did you have insight? You scrolled down. Okay. Well, that's good too, right? If you don't know the answer to something and you know where to go get it, that's good too. Okay. Oh, man. Okay. So there's a couple ways to do this. First of all, we could do very similarly to what we did here. We put it in terms of sine and cosine. You could do that here. You can call cotangent cosine of 11x over sine of 11x, and then cosecant would be 1 over sine of 25x, and then you can like state change flip, and then you can isolate them in their own cells, create what you need, blah, 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 and it'll work, okay? But we can also use the reciprocal identities. We basically have cotangent in the top and cosecant in the bottom. So here's what we could do. A cosecant in the bottom is equivalent to its reciprocal sine in the top, because 1 over cosecant is sine. And a cotangent in the top is equivalent to its reciprocal tangent in the bottom, because cotangent is 1 over tangent. So just by using the reciprocal identities, we now turn it into a sine tangent problem near 0, which we just said they behave the same way, and it's always what? A over B. So this answer does come out to be 25/11. Okay? All right. So we can kind of use the reciprocal identities now to help us so that we don't have to memorize something else. If sines and tangents act the same way near 0, then if we have any combination of cotangents and cosecants, which are the reciprocal of sines and tangents, then we can use what we previously learned. We just have to remember to flip things, okay? And that's where this line down here comes in, right? So if you have any combination then of cosecants and cotangents instead of sines and tangents, it's not going to be m over n as you visually see it in the problem, but rather it's going to be the reciprocal n over m. And now we know why. Yes? Okay? So those are kind of the same if you know the reciprocal identities. All right, and then the last ones down here that I summarized are the second one that we learned. They don't show up as often, but the cosine one, we can commute the subtraction left and right. Okay? So there's a summary. It's kind of useful to have those memorized. Let's see if we can speed it up now that we have those memorized. All right, what about something like this? Is it going to be 14/9 or 9/14? What is it? Neither. Very good. It looks like it should be one of those, right? But never not first. Direct sub. What do you get when you plug in a 0? You get 1 over, what's cosecant of 0? It's dne? Yeah? Why is it dne, though? Right. So if I just put dne there, what would you say 1 over dne is? dne? That would be a great answer choice. Okay? Is 1 over dne an indeterminate form? Not necessarily. No. Let's do the same trick that we just did. Let's go ahead and bring the cosecant from the bottom to the top. So that becomes cosine of 14x times what? Sine of 9x. And now use direct substitution. Cosine of 0 is 1. Sine of 0 is 0. And 1 times 0 is 0. So you could still get it from the first step, okay? Mr. Bird, you said it was the reciprocal of 0, so cosecant was 1 over 0, right? When we use the ordered pair, right? It's 1 over 0. So if you did it that way, now you could do state change flip. And you'd have 1 times 0 over 1, which of course would give you the same answer. So that's why it works. But it probably makes more sense to bring the trig function to the top first. Yeah, good. Now we're kind of like in don't overgeneralize land, right? Don't take those rules and just say, 14 ninths, 9/14. Those would be good answer choices. What about the next one? Yeah, good question. When you plug in, you get cosecant is undefined over sine is 0. So let's do what we've been doing. You want to bring the cosecant to the bottom or the sine to the top? I'd probably bring the cosecant to the bottom, yeah, because we're just a little bit more comfortable with sines, yeah? So we get the limit as x goes to 0. That becomes 1 over sine of pi x times sine of 7x. And now if we plug in, now it's going to give us a definitive outcome, not an indeterminable outcome. We get 1 over 0. And what does non-zero over 0 always mean? Yeah, the graph of that function would have a vertical asymptote there, which forces the y values to either plus or minus infinity. So remember, infinity and 0 are reciprocals of each other. Now, I don't know if it's positive infinity or negative infinity. It's a general limit at 0. So in order to say infinity, it would have to be going up on both sides. In order to say negative infinity, it has to be going down on both sides. So a safe answer would be what? DNE, right. DNE. Okay. Now, you could probably analyze, if you analyze from the left of 0 and right of 0, you could probably figure out what the signs, SIGNs are of those two and determine if it happens to be positive or negative on both sides. But that's not what we're going to do. So these types of questions that we have right here, they could easily show up as like a single multiple choice question or like one final part of a free response. We'll have to stop right there because I think the lunch bell is going to catch us, but we'll pick back up with I. Okay. Have a good lunch.